In this video, I will present a solution to Baltic Way 2022 problem 5. Firstly, I will present the problem statement. We are asked to determine all functions f from real numbers to the real numbers, such that f of 0 plus 1 equals f of 1, and for any two real numbers x and y, the following assertion p of x and y has to hold. F of xy minus x plus f of x plus f of y must be equal to y times f of x plus 3. This problem is concerned with the function f. We are not really given one condition for this function, but really infinitely many. So this one right here, and then one more condition for each pair x and y. To determine all functions f such that all of these conditions are satisfied, we must plug in very many different values for x and y into this equation. In order to maintain an overview over everything that is happening during the solve, it is very important to have nice notation. Therefore, I defined this equation to be p of x comma y before even starting the solve, so that I have really concise notation and can concentrate on what is really happening. We are given information about the values of f of 0 and f of 1 in the problem statement. So let's define alpha to be f of 0. We are going to see this value many times during the solve because we want to use this condition, and furthermore it is a good strategy in general to plug in the value 0 or 1 or things like that into a given equation to start off. Note that we have this term f of x plus f of y right here. This seems annoying in terms of y because we have an f of something plus f of y. Therefore, we will start with setting y to 0. So let's compute p of x comma 0. This tells us that f of minus x plus f of x plus alpha is equal to 3. Call this equation 1. Now let's also compute p of x comma 1 because we want to use that 1 and 0 are interesting values for f. So we get that f of x times 1 minus x, which is equal to alpha, plus f of x plus f of 1, which equals to f of 0 plus 1 or alpha plus 1, is equal to 1 times f of x plus 3. We call this equation 2. Now we take a close look at equations 1 and 2. Note that we have this f of x plus alpha term here and a term of the form f of x plus alpha plus 1. Therefore, it is a good idea to plug in x plus 1 into equation 1 and comparing it to equation 2 and take a look at what this tells us. So firstly, x plus 1 in equation 1 tells us that f of minus x minus 1 plus f of x plus alpha plus 1 equals 3. Plugging this into equation 2 then gives us that 3 minus f of minus x minus 1 equals f of x plus alpha plus 1. This is what we get from this equation. And by 2, this also equals f of x plus 3 minus alpha. And this tells us that f of x plus f of minus x minus 1 equals alpha. We call this equation 3. Let's take a close look at what this tells us. Well, alpha is nothing but f of 0. We have free choice of x on the left side. So what does this tell us if we plug in x is equal to 0 into 3? We get alpha plus f of minus 1 is equal to alpha. Therefore, f of minus 1 equals 0. Therefore, we are motivated to evaluate p of x comma minus 1 because then this annoying f of y term inside here is going to equal 0. So p of x comma negative 1 tells us that f of negative 2x plus f of x is equal to negative f of x plus 3. And therefore we have f of negative 2x plus 2f of x equals 3. A general idea in such problems is that the situation is really nice if all of the terms inside of each function called f are equal. And we can see that we can attain this very easily right here by setting x equal to 0, which is also nice because we are generally interested in the value f of 0, which equals alpha. And therefore x equals to 0 yields 3 alpha equals 3 or alpha equal to 1. Taking a look back at where we used the value for alpha, which we now know to be 1, we see that equation 2 simplifies a lot. It tells us that 1 plus f of x plus 2 is equal to f of x plus 3. Or, in other words, f of x plus 2 equals f of x plus 2. And we call this equation 4. We are going to use two of the results that we have gotten so far to finish our proof. Firstly, that f of 0 equals 1, and that f of x plus 2 is equal to f of x plus 2, which we label equation 4. We know the value of f at 0. Furthermore, we know what happens if we change x with some multiple of 2. But there's not much information about real numbers yet, and all of these integer values, at least of the form 2k, are always going to be 2k plus 1. So to introduce real numbers, we need some real number which is not inside an argument of f. And the only choice for that is this y right here. So we're going to consider general y in our equation. The reason why we haven't done that before is because we had this term x right here, and the best choice for x for now would be 0, so that we only have f of y right here. This tells us that 0 times y minus 0, which is f of 0, which equals 1, plus f of y is equal to y times f of 0, which is equal to y plus 3. Therefore, f of y equals y plus 2, call this equation 5. But in fact, x equal to 0 is now not the only suitable choice in this kind of equation, because we already know that f of x plus 2 is equal to f of x plus 2. Therefore, let's take a look what happens if we plug in 2 for x right here. So p of 2 comma x tells us that, well, 2 times y, f of 2y minus 2 plus f of 2 plus f of y is equal to y times f of 2 plus 3. We are going to use the equation 4 3 times in order to deduce a nicer equation from this. First of all, f of 2y minus 2 is nothing but f of 2y all minus 2. Similar things tell us that f of 2 plus f of y equals f of y all plus 2. And, well, f of 2 is nothing but f of 0 plus 2, which equals f of 0 plus 2, and therefore 3. So we get that all of this is equal to 3y plus 3. Now we have an f of y term right here, which we already know how to deal with. So equation 5 in 6 gives us f of 2y, and by the way, those 2's are going to cancel. I'm just going to ignore them right now. And f of y is equal to y plus 2, and all of this equals 3y plus 3, which is equivalent to f of 2y is equal to 2y plus 1. We recall that this holds for any real number y. So we can just plug in x equal to y over 2 into this equation, which tells us that, well, f of x is just nothing but x plus 1 for all x in R. At this point, if there exists a solution function f to our problem, then it is entirely determined, because at every real number x, if we evaluate f at x, then it has to be equal to x plus 1. So the last step in solving our problem is to check whether that is indeed a solution. So let f of x be equal to x plus 1. Then we see that f of 0 plus 1 equals 2, which is also equal to f of 1. Furthermore, plugging f into this equation tells us that f of xy minus x plus f of x plus f of y, well, this is equal to xy minus x plus 1 plus f of x plus y plus 1, which equals x plus y plus 2. And all of this is equal to xy, the x's cancel out, plus y plus 3. On the other hand, we know that y times f of x plus 3 is equal to y times x plus 1 plus 3, and this is also equal to xy plus y plus 3. Therefore, the left-hand side and the right-hand side of this equation are also always equal, and therefore f of x is equal to x plus 1 is indeed our only solution to the problem.